The background of this talk is that previously I've been working on the detailed mechanical design of instruments, where I put the dichroic and where I make cutoffs and so forth. I'm going to talk about other things today. Generally, I want you to know that I'm talking about a next generation gamma ray burst mission that would image gamma ray bursts in the optical about a second after trigger. The thing you should keep in your mind is the general conceptual idea is to have a scaled down SWIFT, like a scaled down BAT and a scaled down UVOT. And you should just think of it always as just SWIFT and scaled down by some fraction. This year, I've done some work on the image stabilizing scheme, and I've done some work on data analysis to show the feasibility of this mission just by showing that we have a good event rate, and I'll show you how important event rate is as we go along. I'd like to thank my collaborators, George Smoot, and my Extreme Universe Laboratory students, Boris, Igor, and Kirill, who came with me in some internships here and in Korea. And in particular, they actually worked with me on looking at SWIFT data. And so these guys are experienced gamma ray astronomers now. So I just want to remind everybody, if you're not familiar with the NGRG, again, think of this just as a mini SWIFT scaled down for conceptual purposes. It has a coded X-mask X-ray camera to, in a coarse way, localize the GRB, just like the BAT on SWIFT. By the way, people have done studies of the newest, fanciest technology to do this kind of thing. And for example, in this Burroughs paper, they came up with a solution. This is basically optimal because coded mask apertures have very wide fields of view, and they can localize a gamma ray burst to a field size of a reasonable optical telescope. The big difference between this and SWIFT is that we're using a beam steering mirror to point the optical telescope. It's much faster than SWIFT. It points in about a second on target. So just keep in mind this idea of a telescope pointed at a flat mirror. Here's your telescope, here's your flat mirror. You just have motors that move the flat mirror around. You can do that very fast, very accurately. And with a reasonable field size, it's no problem. What about XRT? A lot of people may ask me. Without XRT, you can make about a 150 kilogram instrument. Without XRT, you lose an extremely large amount of the cost and mass of the mission. So I'm trying to think about missions for leaner times, a minimalist mission that would help us all in our science. And so that's why I would be willing to give it up if that's all I could do to have another gamma ray burst mission. Also, there are other missions out there with focused X-ray telescopes that could maybe pick up the slack in at least some of the cases. This is sort of my raison d'etre, the reason I'm in here, is that SWIFT response time cuts off very sharply at 60 seconds. Generally speaking, a UVOT response that makes a detection is about 100 seconds after a burst trigger. And the question is, isn't there interesting stuff to learn faster than that, sooner than that? Ground-based experiments such as ROTC, and of course MASTER, but also Radar and Raptor and all those things have made important contributions to this. But their event rate is generally low, and it's not the right way to go to get, I think, a statistically regular sample. So I always show this plot to get people interested in early emission and remind people what it's all about. Usually there's the strong gamma ray bursts that are the discovery part, and then there's usually a very steep transition to the afterglow. Don't forget about flares, don't forget about jet breaks, all that sort of things going on. In the optical, sometimes you see something similar. Sometimes you see some very strong optical emission and then a rapid transition to the afterglow. But this is the only gamma ray burst that's ever been measured to this kind of detail, to this kind of sensitivity, to this kind of time resolution. And SWIFT has been flying now for what, something like 8 years? This is it. This typical gamma ray bursts are much more faint, and you'll typically see one optical point from UVOT at around 100 seconds. And then the ground-based start picking up dense coverage around 1,000 seconds with important exceptions, of course. But if you look carefully at all those composite light curve figures that people have been showing all week, you'll see most of them do not see the rise. So You could not say, for example, the rise time is such and such. It's always a limit. Some interesting, fun bursts that are sort of classic that are always shown. This looks like maybe there's some kind of correlation between X-ray and optical with some kind of a delay, maybe. This looks like some kind of good correlation, and this looks like nothing. It's a complicated thing. There's things going on, and we need sort of a statistical view of this. I'll talk a lot about my UVOT early sample, which I defined with the goal of getting a uniform set of responses, the earliest possible data in a uniform way from UVOT light curves. Between 2006 May and 2008 October, UVOT responded very uniformly with 100-second W exposure, an open filter. And the exposures began typically 70 to 150 seconds afterwards. And so just make it a little bit of a earlier sample, I required that the midpoint had to be less than 170 seconds. And this is what I got. I want to remind you that sometimes I talk about high time resolution, but I'm always going back to this sample and these results. So in here, I wave my hands a lot, and I'm talking about an average value, and of course, it's not a real instantaneous value. Keep that in mind. 224 bursts went into the sample. 209 made a cut of the kind of operations that Swift did that are real time. There are also image triggers and ground analysis and sky survey sorts of things in there. Those don't work for rapid real-time response. So I threw those out. What I was left with is about 86 gamma ray bursts per year, 38 observations from UVOT per year, and of those observations, 18 detections. I try not to mix detections and observations, which you will see more often. So keep aware that my numbers are very low because I strictly go to detections in the early phases when I talk about all the other instruments and compare. UVOT in a 10-second exposure scaling is sensitive to about 19 mag. ROTC3, which has worked on this for a long time and has presented a lot of fabulous results in papers. They typically, one of the Rykov paper, for example, gave results over several years, I think 5 or 6 or more years. When you come down to it, it's sensitive to 16.9 mag in 10 seconds. In the last 2 years, looking at the GCNs, they've only announced 3 early detections per year with twice as many upper limits. Probably some are not reported, but those are the ones that are early and fast, and detections, not upper limits. MasterNet is sensitive to about 15 mag. Why is that important? Because this is the distribution of those UVOT that I selected. You're just not really in business until you get better than 15th mag. You're barely sampling the majority at ROTC's 10-second sensitivity. You need to get past that to get the majority of these bursts. Again, using the hand-waving argument that a big, wide window will indicate sort of what you're going to see.
I'll just make one short comment. The UVOT wideband is not centered at the same wavelength as the unfiltered observations of ROTC and Master. So the ROTC and Master unfiltered observations are relatively similar to the typical R band, whereas the UVOT is roughly more of a U-band filter in a certain sense. So this is affected more strongly by galactic foreground extinction, by intrinsic extinction in the host galaxy, and by the general color of GRB afterglows. So basically, in a direct comparison, I would say that the white limit needs to be made at least 1 magnitude less sensitive for your generic afterglow than, so in comparison to ROTC. So it's maybe about 1 magnitude better than ROTC in 10 seconds.
Sometimes I'm careful, and I do integrate over the right bands with an assumed optical spectrum, but in all cases I neglect extinction, and of course that's important. I would still say that this means that Swift sensitivity, we need something more sensitive like Swift, and we need a more rapid response to learn more about early emission. We're going to go through a very quick laundry list without discussing any of these things in detail. But if you see no early bright flash in the first 20 seconds, you can say that this, in some sense, supports a magnetically dominated jet, because it's probably not a reverse shock, or it's not a strong reverse shock. If you see a very early, very bright peak, that is what fits with the models of reverse shock emission. If you see a very delayed optical compared to gamma, delayed optical peak compared to gamma, in some sense that supports internal shock, because it's consistent with this idea of an internal shock is down deep in the jet and the optical comes from somewhere else at a larger radius. Rapid optical variability in a very weak way might be suggestive of shocks, because just like you see these very high time variability internal shocks from the gamma rays, if you saw that same thing in optical, if you could look with high resolution, that might in a way be suggestive of the same mechanism. I keep saying, repeating this over and over, with a small fraction of the first 60 seconds of bursts observed, how can we ever talk about these things statistically? I wanted to add one more point, which was from Ehud Nakar's talk. He modeled some shock breakouts in low luminosity gamma ray bursts, and we had an interesting discussion about what you might observe early in the optical, and this might be yet another way to learn things about that kind of a model. I mentioned the external shock, and I would like to thank Alex for pointing out to me this nice paper, which shows very well how if you extrapolate your spectral fits, they're just way too faint for the optical that is observed. In this case, you get a very bright early emission, and so that's suggestive of an external shock model. I'll draw your attention to the fact that there's no rise measured here. I think we've had enough discussion of multi-messenger science in this meeting, but if you want to do crazy stuff like compare the times that different wavelengths arrive, different signals arrive, for example, high energy cosmic rays, neutrinos, and so forth, over huge lever arms like between radio, gamma, and optical, again, you need fast response to do that in many cases. One of my favorite science things you can do, but can only do with fast response, is this idea of evaporation of the dust cloud around a gamma ray burst. People have said that the time scale for this evaporation of the dust around a typical gamma ray burst is about 60 seconds or less. And so if you don't get there with resolution less than 60 seconds, and if you don't get there before 60 seconds, you'll never see this.
There actually is one paper now that purportedly sees this effect. Morgan et al. On GRB 120119A. So they had an extremely rapid response with Peritel and were on the burst in under a minute, and they actually see a relatively strong chromatic evolution in early times where the afterglow is already brightly detected in the K-band. And in a sense, the color is very red at the beginning, and within the next 30 seconds or so, it shrinks down to a color that is then seen in the later afterglow. So this might have been discovered already, just since you don't seem to refer to the paper here.
Honestly, I haven't seen the paper.
Okay,
thank you for pointing that out to me.
Yes, it's Morgan et al. So maybe if you want to find it.
I will definitely do that. The idea here is that if you have an infrared band and you look toward the blue, and you just take a ratio of these two, okay, the colors, then you can learn about the extinction. What's really unusual and particularly exciting about this is that you look at the changing extinction around one star in another galaxy, potentially at very high redshift. There's very few ways we can learn about stars, extinction around stars, around single stars far away, because you always have some kind of confusion, some kind of redundancy between the extinction of the host galaxy and the extinction around the star. I'm going to talk about rapid response science with less instrument, an attractive idea in an age of limited financial support. After Swift, the only well-considered mission that I know about that's going to give us optical IDs is SVOM. That mission is pretty uncertain and very delayed. If you could somehow replace Swift after it's gone, you could have IDs for the community with a fast response and this new fast response science. So ask yourself, is this possible? Again, what do I mean by less instrument? Well, look at all these instruments with $250 million costs, plus launch, $300 million, plus launch, $200 million just for one instrument. We probably wouldn't get much response in the United States from a Congress asking for this kind of money. There exist launch opportunities today. They do exist. Things like piggyback opportunities. UFO is piggybacking on another launch. We have discussed with the people here at Extreme Inertial Laboratory, perhaps, seeing if we could get on a mission like Nucleon on a Resource B spacecraft. And there's the opportunity of the ISS. The problem with these are that they do not point. You cannot make a sensitive optical measurement unless you have some kind of pointing stability. You're looking for arc-second pointing stability. And those kind of spacecrafts are extremely expensive. They're so expensive that only a few are launched per decade. And that's really the trick here. So, to solve this question of how to get a mission that's very modest and can do good science, part one is this idea of just using a flat mirror and a bunch of motors to steer it around. I actually looked in a regular catalog that you can just pull out your credit card and order, and there are motors in very wide ranges of torque, and including some that are approved for vacuum that have control to 0.05 arc-second precision. Not only do they have the encoders that go to 0.05 arc-seconds, but they have a control scheme for them. Very nice prepackaged thing. So you just tell it where you want it to go, and it goes. UFO Pathfinder has already demonstrated about 60-degree slews in 1 second. Using 1 second is kind of a wide, it's kind of an approximate number. Driving the mirror fast enough and driving it accurately enough is definitely possible. Part two of this, the reason you don't need a arc-second stabilized spacecraft, is that you might be doing this by means of a feedback control scheme. Again, looking for about an arc-second. Downward-looking spacecraft typically follow a known path with sort of a smooth motion uncertainty of about an arc-minute, moving on timescales of about a minute. That's a finite problem. Active feedback control for a mirror can stabilize that. And you can get the control feedback from the stars on your field. So you might take a picture, and you might compare it to the next picture and see the stars have all moved. Sorry.
Was anything like that ever launched in space? The moving parts on the satellites are dangerous because like reaction wheels get stuck usually, or filter wheels. Was this ever tested?
The answer is of course it's a matter of degree.
Mission critical.
So for UFO, we have a tiny mirror that's a few hundred grams, and it's on a spacecraft that weighs a couple tons. So you can see that the torque is not going to be a big deal for a typical stabilized spacecraft. It's really a matter of degree, and it's really a comparison of the mode of inertia of the whole spacecraft compared to the mirror, whether or not it's going to be a problem.
I mean, how reliable is this in terms of how is it reliable in space? Is it not going to break in some? Because space technologies, before they can be adapted on a satellite, they have to go through a lot of qualification. I mean, if you're suggesting technology that was not used, maybe I missed the UFO talk, I'm sorry.
I would like to say to you that they're very nice motors and they work a lot for a long time, but of course I haven't tried to space qualify them. Simple answer.
If you have rotation in a satellite and
Once again, it's a matter of degree. If you have a mirror with a very small moment of inertia and you have a spacecraft with a very large moment of inertia, it's not a problem because the spacecraft is always stabilized to some degree. Ultimately, this is an engineering problem and you could always solve this by having some kind of counter-rotating mass, right? But in general, what I've looked at is that on spacecraft with booms and things that move, it's usually not a problem because moment of inertia of the thing that's moving is usually small compared to the spacecraft. Anyways, you're watching the stars move in the frame. You're getting the feedback signal from how they change position. Feedback signal from how they change, you give that to the motor control. It knows the path of roughly the path of the spacecraft. You work it all out, you give a signal to the mirror, and you do it again. You take taking these images frequently, several times, hopefully many times, during each effective exposure.
Okay, so my question is, at some point you'll be limited by how many, by the density of bright stars that you can that you can take images of quickly enough to do this feedback. So obviously, the faster that you want to slew the mirror, the brighter the reference stars that you need. So I mean, is there a fundamental limit for how? I mean, what is the limit for how fast you can slew based on you know how much of the sky you can look at with this?
You get a gamma ray burst, you'll slew quickly to the ref position of the gamma ray burst. Then you're not slewing anymore. You're just stabilizing. Those will be very small motions and they'll be slow.
So for the stabilization, do you just need like, is like one star enough? I mean, it's the bandwidth of your control loop is still set by.
I've never thought about that, but if I had to say something, I might look at the SDSS, find out how many stars there are at each magnitude limit. Say that for a stellar centroid, you signal to noise ratios greater than 8 are pretty easily centroided to 1/10 of a pixel. The number of stars greater than r equals 14 are 68 per square degree in the SDSS, which would give us 5 to 6 stars on our field. An EM-CCD, which I'll discuss a little later, a kind of CCD that has the charge multiplied before it's read out and is optimized for very fast reads, would give r equals 14 at 10 sigma in about 20 milliseconds on a 30 centimeter space telescope. So you'd end up with about 0.13 arc seconds uncertainty in the measurement in 20 milliseconds. There are many more stars at r greater than 14, and you get a 1 over square root of n reduction. Okay, this will work, no problem. There's tons of stars. That's for any huge range of not just frame times, but also even of apertures. If you cut down the amount of light, it's so far from being fine, it's no problem. So how can I convince you that the event rates that I'm giving you are not pie in the sky, since everybody else, when they make a new instrument, they always have extremely optimistic estimates? I used real data from Swift to come up with all of my rates. Detection of a gamma ray burst is dependent on actual light curves and background, because you trigger by peak signal to noise ratio. You don't trigger by, for example, the fluence of a burst. For a scaled down bat, you should be able to make an almost perfect prediction on these detections for any scale smaller than the actual bat, because bat has seen more than any other smaller instrument would see. And signal noise ratio just goes like square root of area. So I ran a trigger algorithm on actual bat light curves. I scaled the signal to noise for the reduced collecting area. And I made predictions based on, and so I really could tell what an identical instrument, but identical, of a given collecting area would see. This is essentially flawed from an astrophysical point of view because it's modulated by whatever Swift operations are going on. If Swift is sick one day, you won't get anything. If the government shut down and nobody can operate, that is reflected in the rates that I get. But at the same time, it's a very real number, and that's why I favored this way of doing it. Again, I used a very, very simple trigger algorithm. I did not go and dig out, the code from Swift or talk to David Palmer or any of that stuff. I just had a simple set of windows, looked in the background. The background is only on one side because in real operation, in real time. You can't go forward in time to look at the background afterwards. You need this, plus you need a little information about what's going on with the spacecraft when the source goes behind, behind the Earth, and when you go through the SAA and so forth. So before BAT can get a location, you trigger BAT typically with a rate trigger. When there are fluctuations in some time window go above n sigma. There are also such things as called an image trigger. They're good for very long, faint bursts. And I didn't use anything like this that would take a significant amount of time or was complicated. I just threw it out of my sample. I used 64 millisecond data channels, 1 through 3 summed. That's a 15 to 100 keV, which gives the highest signal-to-noise combination in the 64 millisecond data. I used time windows of quarter, half, 1, 2, 4, 8 seconds. I used just that one trailing background. And I just went through all the BAT data and determined the point and the value of the maximum signal noise. In our simulation of our X-ray camera, we found that all of our signal-to-noise ratio greater than 5 sources had better than 90% probability of being located on our field. So for us, signal noise of 5 seemed fine. Other people have higher criteria, but we can talk about that later. These simulations were not done by me, they were done by Paul Connell. Whenever, of course, the signal noise ratio gets higher, you get a better location. That should be mentioned. Let's see. So this is incredibly unsophisticated, but I got great results. I only lost a few % by not picking up these other more complicated triggers. And I went through and checked all the time of bursts that I located and compared those to the ones that Swift did, and sure enough, they were real bursts.
What kind of, you're going to use the same detectors, exactly the same, but smaller and same mask?
This is the starting point of this conceptual design, is to use exactly the same detectors, yeah.
So you'll have, yeah, okay. So exactly for the same energy range you'll get.
For this experiment, everything is exactly the same as Swift, just smaller detectors. Because if you start messing with the spacecraft, you get different backgrounds. Right? So I think we're going to have a pretty accurate rate prediction. You can do this for any instrument smaller than Swift, or you get limits for anything bigger. And you can actually use the actual X-ray and optical 2-variable rate predictions here, which is nice. You've already seen this slide. Just to remind you, it was 2006, 2008 when Swift was responding very uniformly. They didn't throw in any strange, filters or other colors or anything. They just went straight to 100-second exposure. So you might currently have observations that look like this. Okay, some data points, and then nothing before about 60 seconds. So I'm claiming that if you have the next data point is as sensitive as the data point before, you can tell something about this burst. If you have an upper limit, you know that's the peak. If you have the same, then you know you're on a plateau. If you have something brighter, you know you're brighter, and you miss the peak. Okay. So using this kind of idea, I said that you detected something or you had something interesting if you were at least as sensitive as Swift was, as the peak that they found. Okay. So early detection is clear. 10-second sensitivity is sufficient to detect the UVOT source that was actually found. By the way, all my rates are based on 10-second exposure times. I'm talking about this kind of stuff and the sensitivity you get in only 10 seconds. So in terms of X-ray rates, I was surprised at how insensitive the whole business was to the actual size of the collecting area of the X-ray detector. You could chop 4/5 of Swift of BAT off, just chop it off, and you would still be able to locate the vast majority of bursts. You go down from, I don't know, your 80 or 90 or what, I think it's probably 90, down to, okay, mid-80s by going down a factor of 5 in the size of the detector. That's amazing. Certainly you pay a penalty for this in terms of the quality of your spectra, time resolution, and so forth, but you can still locate them. X-ray cameras are a very dumb thing. They just collect photons, and when they get a lot of them in some window, then you can go and run a location algorithm.
Analysis, how did you alter the SNR of a given burst to make it look like a smaller detector?
Just scales with area, right? Scales to the square root of area.
No, but what did you do to the Swift data to make it look like the detector was smaller?
Just scaled the signal to noise by the square root of area.
Scaled what by signal to noise?
If you have a signal noise of 10 detection, what's it going to be in a detector that was half the size?
Okay, so all right.
And of course you throw out any that then go below 5. They could go below 5 or 6.5 or 8.
So what I was asking is if you like took some sample of the background noise from beforehand and added it onto the on-source area to decrease the signal-to-noise ratio.
So when you have a smaller detector, right, you get less background and you get less signal. Okay, but the signal and noise is worse because you have less collecting area.
Oh, right. Yeah. Okay, all right.
Okay. So anyways, remarkably insensitive to the detector collecting area. Okay. This is for rate triggers only, right? So I claim that you could have lots of detections with 1/5 of the Swift's collecting area, much smaller instrument, much less mass, okay, and maybe you can get it on a piggyback satellite. There's a well-known correlation with lots and lots and lots and lots of scatter between fluence and afterglow optical.
So if you lose the burst, will you first lose the higher energy burst also? Because, I mean, then you don't lose so much burst because you collect photons at lower energies. Then if you lose this burst, you collect less bursts that are predominantly at higher energy. So, I mean, the population of bursts is going to be the same or not? Because it's not going to be exactly the same, probably.
I think that, I haven't really looked into it. I think it's going to be almost identical. I think that the vast majority of Swift triggers are kind of like this. They just look at a big number of co-added channels. I think they add other circuits that look for interesting things, but I think those are statistically small.
Okay.
So the question is, does this have some kind of major effect on detection, on detecting optical? Okay, and the answer is, for me, was nothing. When I binned the log fluence versus the probability of detection, I got flat. So these purple dots are the fraction of UVOT observations, and these are the fraction of UVOT observations. These are the fraction of total bursts. And it's more or less flat in fluence, and probability of detection is more or less flat in fluence, and these have very large error bars. So if you see a little dips, those are not significant.
Coming from the fact that the lower luminosity gamma, like from basically the luminosity, like lower luminosity gamma ray bursts are more abundant, so you see them at closer distance, or why is it flat?
You look at the UVOT data. Sometimes you sample the bright part of the curve. Sometimes sometimes you're too late and it's already faded. Sometimes it hasn't come up yet. I think there's just lots of different strange things going on. And that is very...
So you say no definite conclusion can be made from that.
Yeah, but I think the correlation is destroyed because you're not sampling a uniform part of the light curve. When you look at that, when people do these correlations, they always pick something very uniform. They pick before jet break, after jet break, where there's no flare, something like that. And then the correlation looks good. It's very uniform. Here, it's very non-uniform because there's a lot of stuff going on. It appears to me that this reflects the fact that some bursts peak very early and some don't, and it doesn't seem to be strongly related to the fluence. So, remarkably insensitive to X-ray collecting area, but absolutely not to optical area. It seems to me that unless you have a telescope, an aperture as big as Swift, you're going to be severely penalized in rate. So for my 20 centimeter telescope, severely penalized in rate no matter where you do in X-ray area. This is all for 6.5 sigma criteria in between. But the good news is that with 1,000 square centimeters, you're still getting a dozen detections a year. And over 5 years, that would be pretty interesting, right? 60 bursts. Remember, we're here. But we can do a lot better than this. We went from 18 down to 13 per year, 18 of Swift down to 13 per year in that figure, because we went to 10-second exposures. Again, in my following, Swift is an exact identical copy of Swift. But Swift has terrible quantum efficiency. It's just awful. They're using a very old microchannel plate as the first surface detector. You can get much better quantum efficiency than that, and this EMCCD that I proposed earlier for fast frames is at least a mag more sensitive. You get 4 times as many photons. Okay, folding in that, you are back up to 16 GRBs per year if you just use an EMCCD instead of the microchannel plate and intensified CCD that Swift uses. Again, these are only 10-second exposures. This is the quantum efficiency of the UVOT, and this is a Princeton EMCCD.
EMCCD. Do you have any? Do you know any one EMCCD with a flight certification to space?
I haven't looked into that. I don't think it exists. A near-infrared broadband camera, which I mean really broad, I mean 0.9 to 1.8 microns, can be incredibly sensitive in space. It's 2.8 mags more sensitive for gamma ray bursts with a minus 0.75 spectrum. This is proposed by Raikoff et al. You could detect every UVOT source with an additional 5 magnitudes of AV. Okay, because with integrating over the near-infrared band, okay, you're much less sensitive to dust. Remember, Perley has actually proven that you can boost your event rate by looking in the near-infrared, because in his paper in 2009, he looked at 29 Swift gamma ray bursts. 15 were detected by UVOT. He went back and he pounded on them with near-infrared, and sure enough, he found 8 more. That's a huge increase in rate. 8 additional ones out of the original detected 15. Okay, so.
Maybe just one short comment here. There's also the paper by Jochen Seiner from 2011, which looks at the 4-hour sample from Gront, and I think for all GRBs that were observed within the first 4 hours after the burst from Gront, over 90% were detected, especially also due to the infrared capabilities of Gront. So basically anything that is not extremely faint or extremely extinguished is going to be able to be seen in the near infrared.
So this is I didn't have those numbers. I thought that Perley's paper was based on mostly ground data, but anyways, no. Okay, no. What did he use?
Stuff.
His own stuff. Okay. At any rate, this is the rate factor that I used. I'd love to double the number. That would be even better. But I get then 25 detections per year in the near infrared. Okay. So that's pretty neat. I probably didn't discuss this in detail, but okay. You have your mirror, and you have. It's okay. You have your mirror, and you have 2 cameras separated by dichroic. And so you can look in these different bands simultaneously. Okay. Back to this, my favorite scenario again of this evaporating dust, which may have already been observed. If you just take a ratio of the optical flux and the IR flux, of course, you can derive a kind of AV, and you can learn something about extinction. And you can, this is dependent on the redshift. Here's a few curves I've made of that. Okay. But you can start to get a handle on this stuff by doing this. And it's because near-infrared cameras in space are just incredibly sensitive. But we can do better, still. Because Swift, BAT used CZT, which has a low energy threshold of 15 keV. Okay, the SVOM team is using cooled cadmium telluride, and it's not cryogenic, it's just cold, minus 20 C. It probably gets colder than that in Moscow. And they got a low energy threshold of 4 keV, and I'm actually quoting a private communication because he actually showed me the data, and you can really see down to 4 keV. I'm not going to go further in predicting a rate based on this because I don't know the low energy background. Okay, but you know, the DXRB is not going to somehow swamp you. I would be very surprised if the low energy background were, you know, many times more terrible than it is at above 10 keV. So I think you would get a huge jump in signal and noise, and I think you could get even more bursts by just going to a low threshold detector. Somewhere I was supposed to say that, thank you. You get a factor of 6 in photons by going down to 4 keV. Factor of 6 in photons, source photons. Okay? So this is going to be good stuff. What about other instruments? What if it was an exact Swift copy? Okay? So that's very important. I talked about putting something on the ISS. The ISS passes through high background regions because its orbit is not perfectly equatorial, it's tipped. So it'll pass through the tip of one of the Van Allen belts, and it goes through the SAA. In practice, an X-ray camera has about a 50% duty cycle on the ISS. I got that from Maxi people, from Motoko Sonino. UFO Pathfinder, which you've heard about earlier this week, is in a polar orbit. That's really bad for X-rays. You pass 4 times through belts. Okay? When looking at the background of Swift, you can see that the decay time is about 1,000 seconds. So for a 5,000 second orbit, that's a big problem. 4 passages for 1,000 seconds, 5,000 second orbit, big problem. With a very rough estimate, not having looked at a study of this, you can guess that the duty cycle is going to be about 20%. And so it's hard for me to believe that UFO is going to get more than 4 gamma ray bursts per year, and be real lucky if it got one optical detection with its little 10 centimeter ICCD.
Just a short question. This is probably completely utopian, but have you checked out what the launch costs are to get such a satellite either into a very high integral-like orbit or maybe actually put it at L2? I mean, that would be fantastic because then you would not have any Earth occultation, no radiation belts, nothing. You would have basically 4 pi steradian and...
Yeah. No, I haven't because it's not realistic. It's not going to happen. I need to do lots of instrument work. I still have to do simulations of feedback control and an optimum frame rate, get more information on spacecraft motion. I still have to estimate the low energy background to really calculate a boost in rate. I want to find more uniform samples for shorter UVOT exposures. Remember, I was lazy and I didn't go in and actually go into UVOT and actually slice up these exposures into shorter time frames and tell you what would really happen. See what the peak really is and so forth. I just haven't checked into that yet. So to summarize, early emission is complicated. There's prompt emission, there's transition, there's flares and peaks, which will mess up all of this, especially if you don't have the time resolution, but you can get it if you do have the time resolution. There's possible signatures of emission, which would be great to statistically quantify. It's feasible to have a small satellite that can go do all these things. 1,000 squared centimeters with a 30 centimeter optical aperture and 10-second exposures will give you 16 optical detections and 25 near-infrared detections. You'll get a source of IDs for the community, which I think is really important in the Swift has got to die someday. You'll be losing in your X-ray time resolution and your time resolution in the X-rays and your X-ray spectra, because if you throw away photons, you lose. That's it. It's not going to be as good as bad. But you get most of the Swift optical ID rates. and that's really interesting. The statistical view of this first 60 seconds is what we're after, and in addition to that, you get all this new rapid response science. I'm going to note that you do this with an old Swift population. People don't like that. They want to build a new instrument that can do new stuff. They want to see higher energy population, this, that, and the other thing. Okay, but it's still new science with the old population. So thank you very much.